say V1, V2, V3, V4. Is this isomorphic to, I don't know, let's call this U1, U2, U3, U4. I don't know why that way, but that's just one way of numbering these vertices. Are these two graphs isomorphic?
Yes.
Okay.
Yeah.
So,
Yeah.
Because if we map V1 to, let's say, U1, and then V2 to U3, and then V3 to U2, and then V4 to U4, then they have the same kind of, let's say, neighbors, and they connect the same way as they did in the first graph.
Right. So that's correct. So let's summarize this. Can we summarize the definition in one sentence, right? In one or two sentences. So first of all, we need this mapping between the vertices, right? So this mapping itself is from this. This is what kind of mapping is this? From the vertices of the first graph to the vertices of the second graph, right? So here's the first graph. Here's the second graph. So I'm mapping this.
You mean the one-to-one?
Yes, it has to be one-to-one. Okay, so it has to be a one-to-one. What does that mean, that it's one-to-one mapping?
That it has exactly one, like the function has exactly, that takes an input, gives one output.
Yeah, well, any function has an input and an output. But one-to-one means that distinct elements map to distinct elements, right? So if I have two different elements here, for example, V1 and V3, they better map to two elements that are distinct also. So they cannot both map to the same one, to the same element. So for example, x squared function is not one-to-one because like these two distinct elements map to the same. So -3 and +3 map to 9, both of them. So if a function is one-to-one, I cannot have that kind of mapping. Distinct elements should always map to distinct elements, like in a linear function, for example, like in a cubic function, right? So from calculus. So here, distinct elements, this mapping that you showed us is that distinct elements map to distinct elements. That's called an into, injective function also, but the term is not that important. But it also is an onto function, sometimes called a surjective function, which gives us what? What's the name of the function that is one-to-one, as you told us. So distinct elements map to distinct elements. And also, everything in the image gets mapped to. There's nothing left here.
That's a bijection.
It's called a bijection. So a bijection is this one-to-one correspondence where if we have two sets of elements of the same size and distinct elements map to distinct elements, we have a bijection. The vertices of these graphs, the set of vertices of the two graphs, if I'm to show that they are isomorphic, better have the same number of elements. Okay, so we just showed that this is a bijection. This is indeed a bijection. This mapping that you showed. But for an isomorphism, we need a little bit more than just simply showing that the mapping is a bijection. So it's not sufficient for us to show a bijection between the vertices, this mapping between the vertices, and claim that the two graphs are isomorphic. It's necessary for us to be able to do this, but not enough. What else do we need to claim? We need a stronger condition. We need to claim more in order to know that the two graphs are isomorphic. And you told us, so it should preserve this adjacency relationship, right? So under this mapping, two vertices, and this is an if and only if statement that I'm about to say, the two vertices, if they're neighbors in graph G, they must map to the two vertices that are also neighbors in graph G2. And moreover, the converse is also true. If they're not neighbors in graph G1, then their images must be not neighbors in graph G2. So this is the condition that needs to be met. So for example, this bijection that you gave is an isomorphism. It's just not simply just a bijection, but it's also an isomorphism because check any two elements. So V1 and V2, for example, are neighbors here. Here's V1, here's V2. They're neighbors connected by an edge. Their images are U1 and U3. Here's U1 and here's U3. Those are connected too. In fact, any pair of vertices that you take here that are connected by an edge will be mapped to a pair of vertices in G2 that are also connected by an edge. And conversely, if you take two vertices here in graph G1 that are not connected by an edge, like V1 and V4. Let's take V1 and V4. They're not connected by an edge. Then they must map to vertices that are not connected by an edge in the image graph in G2. So for example, V1 maps to U1, here it is. V4 maps to U4, here it is. Those guys are not connected by an edge, this guy and this guy. And that should hold for every pair of vertices. Does that make sense? That's what an isomorphism is. An isomorphism is such a bijection where this adjacency relationship is preserved. So that's a definition. So let's see, are these two graphs isomorphic? I just gave you the answer. So let's think about it if you haven't seen the answer. If you have it in front of you, don't look at the answer. Let's just think about it for a second. What do we have with these two graphs? So first of all, we must have a bijection between the vertices, right? So unless the two graphs have the same number of vertices, no bijection can be shown to exist. So they better have the same number of vertices. So this mapping is going to be, so G1, let this be the set of vertices V1. So V1 includes A, B, C, D, blah, 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 and their edges, and the edges that you see there. And H is this collection, the second set of vertices with its own edges. So what should this bijection be? It should be a mapping between V1 and V2. Well, we do have the same number of vertices here. Both graphs have 8 vertices, so that bijection can exist. I mean, that bijection exists. I can set up a bijection. But can I set up an isomorphism? Well, let's see. It's pretty promising when you look at it. Okay, so what are, first of all, is it obvious to people that if I'm to have an isomorphism between two graphs, then the vertices of a vertex of degree 17 in graph G must, there's no other way, map to a vertex of degree 17 in H as well. So whatever the degree of a vertex is in G, that vertex is mapped somewhere. That somewhere vertex better have the same degree. Otherwise, the neighborhood relationship will not be preserved. So we need to preserve that neighborhood relationship. So that means, that already implies that the degree sequences of the graphs must be identical, right? Help me out. So what's the degree sequence of a graph?
Of G1?
Yeah, of both, yes, of G1. Sequences of G1. Of G1.
So starting at A would be 2.
Yeah, so we'll list, in the homework exercises, was the degree sequence defined as a non-increasing sequence or a non-decreasing sequence? There's a preference of writing this down somehow. How did you write down this in the homework assignment?
It was from 1, 2, 3, if I remember.
So it was a non-decreasing sequence. Let's write it down that way. So what are the sequences here? 2, 2. So help me out. So what are the degrees in G? This guy has degree what?
2.
2. This guy?
2.
2.
And these guys?
2.
2.
Okay, so I have 4 vertices of degree 2.
And then I have 4 with 3.
3. That same sequence is the degree sequence of H as well, right? I have H and G here. Okay, so let's call it G and H. So G has the same degree sequence, right? So that gives me more hope that an isomorphism can be found, right? So the degree sequences, so now I'll be mapping those vertices have the same degree to one another somehow. Well, because if I have an isomorphism, well, if the degree sequences were distinct, then that's it. All hope of finding an isomorphism is lost, right? Because there will be some vertex with some neighbor whose counterpart is not found in the other graph in H. So here, the promise is still there. Well, also, was it clear from the homework assignment that if two graphs are isomorphic, if I'm to build this mapping, this isomorphism, that there's a bijection and preserves this neighborhood relationship, if I am to find this mapping, then the number of edges must be the same, right, in the two graphs. Because what does an edge signify? It stands for neighborhood. Okay, it signifies the neighborship, if you can call it, the relation between two vertices, right? And the two vertices are connected by an edge if they're neighbors. It's by definition, that's what it is. So they better have the same number of edges, because neighbors are mapped to neighbors and non-neighbors to non-neighbors. So the two graphs, if they're isomorphic, they must have the same number of neighbors, edges. And these two graphs have the same number of edges, 4, 4, and another 2, 10 edges. Each graph has 10 edges. So it's pretty promising that we can find a mapping, but does it exist? Okay. Now we have to cleanly argue. If you see this exam, if this question on the exam or on the quiz, and you will have something similar, if they're isomorphic, you should write down the isomorphism. Should write down the isomorphism. So if they're isomorphic, I want this F explicitly written down. That tells me that A goes there, B goes there, C goes there, and so on. D, E, F, G. That's it. So G, that gives 7. I need an H. Don't I have an H somewhere? Yeah, I need an H. Okay, so these guys map to somewhere, to the degrees of the, to the vertices of the same degree. So A better map to a vertex of degree 2. So how many choices do I have for an A? If this mapping here that I'm writing down on the right-hand side, if that is to be an isomorphism, how many?
4.
Yeah, I have 4 choices. What are they?
It's the A, X, Y, and I can't say those two.
Yeah. Oh,
T.
do you guys see this? You guys can see this screen, my screen, everyone?
Yeah, it should be the S, T, V, and or U.
Yeah, yeah. So I better map to,
A, not I.
okay, map to either T, U, X, or Y, right? There's just no other. Other degrees have, other vertices have other degrees. Okay. All right, so, but what else? I'm kind of stuck. So what? Okay, so I know where A must map to. Okay, that's just an observation. Are the two graphs isomorphic, or they're not?
Also, A has to be neighbor to a 3-degree vertex. To 2 of them, actually.
Okay, A's neighbors, A, let's write it this way. A is adjacent to 2 vertices of degree 3, right? 2 verts of degree 3, right? Is that what you said? Right?
Yeah.
Now, for the 4 choices that we have for where A must be mapped to.
It's W, S, V, and Z.
Yeah, X and, no, Z has the degree. You mean X and Y?
Oh, wait, you're talking about the 4. I'm sorry.
Yeah, so
I thought you meant which ones can be mapped to.
Yeah, which ones can A map to, as we just wrote it down. I'm just saying these guys. But what are the neighbors? So, but T has neighbors of, what are the degrees of the guys that are T's neighbors?
One is 3 and the other one is 2.
Okay, degree 2 and 3. So I cannot map A to 3, A to T, right? Because both of A's neighbors are of degree 3, and T has a vertex of degree 2. So that is it clear that I cannot map A to T. Okay. So how about you?
How about me?
Yes. How about this U that's on the screen?
It's mapped to the same. One is 2, degree 2, and the other one is degree 3. So it cannot be.
That's exactly correct. So I don't know why I copy pasted this instead of the first line, but here it is. It's still clear. So this is, but this is happening. So can I conclude from there, from this, from what's on the screen, that A cannot be mapped legitimately to meet the definition of the isomorphism to any of the vertices? Because the only 4 choices I had were T, U, X, and Y, and none of them fit the definition of an isomorphism, of isomorphism, right? So A cannot be mapped. So this is proof that these 2 graphs are not isomorphic, And notice what's happening here. Both of these graphs have the same number of vertices, have the same number of edges. Their degree sequences are exactly the same, but there is no isomorphism between the two. They're not isomorphic graphs. Okay, so it makes sense, this example? Okay.
You have to just write those 4 statements just showing that the mapping.
Yes, yeah, an argument something like this. Yes, they cannot be isomorphic because, and you write this as just one paragraph. So,
okay, so you don't have to do the number of vertices and edges and so on.
No, you don't have to write it this way. No, as long as it can be like completely in words.
Okay.
You can say, like, you know, if it's as long as it's clear, right? You know, the whole purpose of these symbols is to simplify conveying the ideas, right? The process. If you can write it down in words without using symbols, all the better. It's fine. Either way, it's fine. Okay, so let's move on. This is slightly simpler. Are these graphs isomorphic? Are these 2 graphs isomorphic? So by the way, on the tests, you will usually be able to somehow manipulate the graph in your mind's eye.
Yes, they are.
Okay, how so?
They are.
Well, should I prove it, or can I just say how I thought about it?
Yes, how did you think about it?
I moved U2, vertex U2, into the kind of a middle where V2 is.
Okay. Now I started moving V's, so let's do it that way because it's already on the screen. It's the same thing. So notice what I'm doing here is it's the same thing. It's exact. So V6, I moved V6 up there. So this is V6, V6. And then you have, well, V6 is connected to V3 and V5. So you have that. And then you move this guy here inside. So either way you want to, this is just one way of seeing it. I don't know if it's just one way. So you have V2, and now it's clear that the blue thing now, first of all, this blue thing, or whatever this color is the same as this guy, right? And now it's easier to see that these are the same. By the way, the sign for isomorphism is this. This is just a symbol usually used, but you don't have to use it. But it comes from algebra, and there's a notion of isomorphism. There's a more general notion of isomorphism that in abstract algebra you may have seen if you've taken abstract algebra courses. Okay, so any questions about graph isomorphism? Let's now we have to move on. There are a couple of things that we need to talk about. Let's move to chapter 10.4. Now, I would like to define a few terms related to graphs again, okay? So you certainly know already what a vertex is, what an edge is. We want to talk about paths and graphs. And closed paths like this, and I haven't, so a path is simply a sequence of edges like this, E1, E2, E3, etc., such that they are connected, they're attached to the vertices like this, okay, so that E1, so the left end of E2 is the same as the right end of E1, so that you can traverse the path like this. So for example, so it's a very intuitive notion. So you start, let's say this is V1 here, V2, V3, V4. This is what Rosen calls a path. A more general term in literature is a walk on the graph. Okay, so V1, V2, V3, V4, that sequence of vertices just specified just by these vertices alone, which is sufficient. It is sufficient to list just the vertices if you don't have more than one edge between the same pair of vertices, right? If you don't have a multigraph, there's exactly one edge between any pair of vertices at most. So if you're specifying a path, it's sufficient to simply write down the sequence of vertices, and that will give you a path. As long as between two consecutive vertices on that list, you have an edge, it will give you a path. Does that make sense? It's a pretty intuitive notion what this is. And if the first vertex happens to be the same as the last vertex closing the path, then such a path is called a cycle or a circuit. Now, I must tell you that there is considerable variation in terminology as you Google stuff about graphs and as you read any given textbook. It is more standard in math graph textbooks to use the term walk as a, so here's a slightly different terminology from Rosen's. Okay, we'll eventually we'll use your textbook's terminology, but I want people to be aware of these differences. So let's look at it. And I'll tell you how this exactly corresponds to Rosen's definitions. So a walk is the most general way of traversing the graph, of walking around the graph. What is a walk? It is just, okay, it is any sequence of edges here, okay, where each edge starts, okay, where each edge, except for the first one, starts at a vertex where the previous one ended. Okay, this is what I actually talked about here when I was talking about this path, when I wrote this down. But notice what's happening here. It's general. Why do we say it's more general than the other definitions I'm about to give? You can traverse any edge or go through a vertex more than once. So for example, let's take this one, which meets the definition of being a walk. It starts at X here, then it goes to Y, then it says W, then it goes to Y again, traversing the same edge in the opposite direction. Then it goes to V, then it goes to W. So this kind of traversal is a traversal, this particular traversal is one where this edge, W, Y edge, was traversed more than once. Okay, let me stop for a minute. Did everybody sign in? I want to.
No, I didn't.
Please sign in. Please sign in. Okay, so a path. Okay, so let me write down what Rosen says. So Rosen gives a name. This is very confusing, but I want to tell you nevertheless. So Rosen calls this a path. This walk is a path. In that context, then, in Rosen's context, what we'll now call a path isn't going to be a path. He calls that a simple path. Okay, so now in this context, a path is a walk that does not repeat any vertices. So this walk here, okay, it starts at U and goes to W, then goes to Y, then goes to V. No vertices were repeated. No vertices were repeated, and that's called a path. Okay, and finally, a trail is a walk that does not repeat edges. Okay, so here's U, W, Y, X. Notice what will happen now. I will pass through the vertex more than once. What was that? X, so it started here, X, now XW, and then WV. So this vertex was passed through more than once, but no edge was traversed more than once, unlike the previous example. Did people see this? So notice that's kind of, it's not even a subtle difference. It's an important difference. So you can have walks where you traverse every edge at most once, or exactly once in the whole graph possible, but no more than once. You traverse the edge, any edge, no more than once. And you can have a walk where you pass through a vertex no more than once. Okay. Now, can I ask you the following? Is the following true? If you have a trail, you also have a path. Is that statement true? So again, the trail means you're covering the edge at most once. Is it possible that if you're, okay, so you're covering the edge at most once, is it possible for you to pass through the vertex more than once? We just had an example of this. Is it possible?
Yes.
Yes.
Can you repeat the question?
Yeah. So here's what I want to claim: that every path is a trail, but not conversely. This is what I'm getting into. So if you have a trail where you hit every edge at most once, it is possible that you pass through a vertex more than once. We just had this example when we went through something like this, right? So we passed through this vertex more than once, and we didn't hit any of these edges more than once. Right. However, conversely, if you have a path that is you go through the vertex at most once, can you go through an edge that's attached to it more than once? Is it possible? I mean, you just went through to that vertex just once, it may have like 50 edges attached to it. You won't, if you just pass through that vertex once, at most, you're using up 2 edges that are attached to that vertex. You're not using the other 48 at all. So the point is that if you go through the vertex just once, then you are using all the edges at most once. So you have a trail, right? You come through one edge, you leave through another edge, and you never see that vertex again. So there's no danger of you traversing the same edge through which you came to that vertex or through which you left that vertex. Does that make sense? All right, so, okay, so in this graph, there's a little bit of an exercise here. Is there a trail that is not a path? So what am I being asked here in this terminology? Can I find a trail? We already did it. I actually did it.
Yeah.
We just did it.
The example of a trail is not a path.
Yeah, so this was a trail, for example. That was not the path according to this definition. Now, in Rosen, this is called a simple path. So we'll always be clear with this definition. So later today, we'll talk about something called Eulerian trails. Okay, let's actually talk about this now. These slides now in chapter 10.3, I think I want to skip a bunch of things, right? About connectivity. We need connectivity, but I have a bunch of proofs here that I'm going to skip about connectivity. So we'll see what we'll be skipping here. But let's talk about graph traversals a little bit more. So here, let's go here. So in the 18th century, this is mid 1700s, 1750s or so, in this town here called Königsberg, this is where Euler lived. The people on the weekends would wake up and they would stroll around their small town. And the river that runs through the town has a few bridges built on it. And here's the layout of the bridges. So by the way, this is the map from the 1700s here, and you can see all these bridges here. And here's a nicer representation here. It's clearer to see. Okay, so the question was this: can somebody start a walk anywhere in such a way that they cover every bridge exactly once? So something like that. Now, this is not going to be because I missed this trail, but is it possible? Maybe there's some way for me to traverse this. Oops, I ended up in the wrong place. Traverse this in such a way that I'll cover every bridge exactly once. Now, ideally, you may want to start and end at the same place, but doesn't have to be. You can start here and end there if you want. The point is to hit every bridge and don't go through the same bridge more than once, right? So you're on this leisurely walk, and you don't want to be in the same place. You just want to see the whole thing. So you're just walking around. Right? So is it possible? So let's give it a shot. Let's take 2 seconds here, 2 minutes here. Just try it out. Can you do it? You guys see my screen, right?
It doesn't seem possible, but I could be missing something.
What is it? It's possible?
I said it doesn't seem possible.
Doesn't seem possible? Okay, but we need, okay,
Well,
anyone else?
Can we argue that with the number of vertices, that's the land, and the bridges or edges that we have?
Yeah, so I don't know if are you building a graph like this? It may be helpful to this. You were building a multigraph like this, which I have on the next slide. So this may be what you had in mind.
Yeah.
Like this. So you have these vertices, like, I don't know, A, B, C, D, I don't know how you, so you have a graph on 4 vertices, and it's a multigraph. So let me show you, it looks something like this. Let me actually see it. Here it is. Okay, so yeah. That's the guy, Euler, by the way, one of the most prolific mathematicians of all time. It's from the 18th century. Okay, so he's the guy who wrote a paper in the 1700s. Very few people would read it at the time because it was written in Latin, right? But you can read it on the web if you can read it in Latin, his original paper. Okay, so I'll give you an argument that he gave in his paper in a minute. Okay, so you model, this is what started graph theory, by the way. Historically, this problem is credited as problem number 0 of problem number 1 of graph theory. So as you've just suggested, you identify each landmass with a node in a graph, a vertex in a graph, and you build a graph exactly like this. So A is this piece of land, B is this piece of land, this is C, this is D. And then these bridges, it's quite intuitive. The bridges correspond to the roads, right? So the bridges are the ways, and those are the edges. So what does the problem of being able to walk around town so that you will traverse each edge exactly once correspond to in terms of this graph language? So Euler at the time didn't have the graph language. Now we do, so we can simplify this. We can more simply, given that the language and terminology exists, it's much simpler for us to state the problem, to say what we're talking about in terms of this graph. What are we talking about? Is there a
It's
way?
actually defining a path.
Yes.
But this path has to go through every single, not vertex, the other, like edge. Every single edge, yeah.
Exactly. So we call that a trail. So when you do these that's why I wanted to talk a little bit about that terminology. Although
trail, yeah, not path, sorry, trail.
Yeah, trail. So according to that terminology that we just talked about, this is called an Eulerian trail, finding an Eulerian trail. What that means, in a slightly more verbose way, is you want to start at some vertex here. Doesn't have to be vertex A. Start at any vertex and traverse the graph in such a way that every edge is traversed exactly once. And the question is that possible to do in this graph? So if I'll give it a shot. So here's my best attempt here, maybe this way. And now when I'm here, kind of stuck, because if I go there, this edge is not traversed. And if I go there, then this edge is not traversed. So maybe I started at the wrong place. Maybe I could have started here. Maybe I'm doing something wrong. I just can't do it. I can't do it. So why is that? That's what we want to determine. Why is that?
It seems like there's a problem with there being so many odd degrees.
Oh, okay.
I'm not exactly sure how to say it, but that seems like it's a problem that when you pass through, like there's always that extrovert edge. Because
but having an extra edge,
we can't meet it without going through the vertex an extra time.
Okay, so that's it. So the hunch is correct, but although we now need to talk about this, write this down somehow. I want to tell you what Euler said before I tell you this. Actually, let me tell you this first. It's similar to what he said, but I wanted to give you his argument, but it doesn't matter. It's in the handout, so it's just basically his paper. So suppose there is a way of traversing this graph. So here's the graph. Again, suppose there is a way of traversing this graph in the way we described. So what is the way again? Every edge, every bridge is covered exactly once. Now, it must start somewhere and end somewhere, and that start and end may be the same place, but it could be different places. Okay, so suppose you have like a start place, start landmass, start vertex in this graph somewhere, one of these 4 vertices, and an end vertex. Could be the same vertex, could be different, doesn't matter. So you have some kind of path like that. Now, let's look at any vertex or any node that's internal to that path. And let's see if there is anything that we can say definitely about that vertex. My claim is that that vertex cannot have an odd degree. Why can this vertex not have an odd degree? Well, suppose it has an odd degree. Suppose it has
because it's a corner. It's not a corner. It's not
because it's not a yes. So okay. So suppose this guy had degree 3, right? So degree 3, because it's an internal vertex, I must use one of these edges to come in to that vertex, right? It's on the path, and another edge to leave it. Not the same edge, another edge to leave it, because I'm covering every edge at most once. So I've just used up one edge. I can't go across that same bridge anymore, so I'm using another bridge. So when I go through this vertex, because it has the third edge emanating from it, and that edge must be used up as well, I will end up coming back into this vertex again. And then there's no way of leaving it. So you're stuck in a black hole then, right? There's no way, you were just sucked in. There's no way out, right? Does that make sense? So it cannot possibly have an odd degree of 3. And if the degree is 5 or 7 or 31, the same applies. You go through it as many times as you have edges, but then the last time you have to, when you come in, and you do have to come in because you have to cover every edge in the graph. Eulerian trail means that you cover every edge in the graph, right? So every bridge must be traversed. Then you come in and you get stuck. So what happens is that no internal node can have a degree of an odd degree. Can have an odd degree. So every internal node must have an even degree. Do people see that? That's just simply a logical conclusion. Now let's look at this graph. What are the degrees of the nodes?
3, 3, 3, and 5.
Yes, so I have no node of even degree. So essentially I have no internal node. Given what we've proven, I cannot possibly have an internal node. So a path like that cannot exist. Does that make sense? So if I'm to have an Eulerian path, I must have all these nodes of even degree, right? In fact, what's happening is that in a graph, there is an Eulerian circuit. And this is if and only if statement. I'm not proving it both ways, but one way it's easy to see. And you should read the handout also for a stricter proof. I'm not going to be asking you for strict proofs. But here's the following thing. Following is true. In a graph, in a multigraph, and we're talking about undirected graphs. It could be these are multigraphs. So you have multiple edges connecting the points. You will have an Eulerian circuit. What's a circuit again?
It all connects, like all the vertices.
Well,
but it returns back to like the original.
Yes. So the circuit means it returns to the same vertex where it started, right? So that's by definition, it's a circuit. And again, this definition, just have it on the side. The first few times you use those definitions, it kind of takes a moment to get used to it. Okay, so a circuit is a path that starts on some vertex and ends at the very same vertex, right? That's a circuit. In order for there to be an Eulerian circuit, meaning you cover every edge exactly once and start and end at the same vertex. For this happens if and only if every vertex in that graph has an even degree, right? So we only can. It's easy to show it to see it one way, as we've just argued, but it's an if and only if statement. Okay. For you to have a path that starts at some vertex and ends at a different vertex, not the same one, some other vertex. For you to traverse this graph in such a way that you hit every edge exactly once, that is, traverse it, find an Eulerian trail on this graph, it must be the case that you'll have exactly 2 vertices of odd degree and every other vertex must be of even degree. So that's a theorem. Call it Euler's theorem. Okay, so let me give you an example of another graph so that this makes complete sense. So some of these bridges were destroyed in the war, in World War II. So by the way, this is no longer Königsberg. This is the city of Kaliningrad today. It's no longer in Prussia anymore. Hasn't been in a while. Some of the bridges were destroyed in the war and in World War II. Others were built over time, blah, 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 and so on. So right now, if you do Google Earth, you'll find the same city. So this map there was from the 18th century, 1700s sometime, and this is like Google Earth now. What the graph now looks like is this, just like this. Okay, so now is there an Eulerian path? And like 2 centuries later, after all this history.
Yes.
Okay, so where is it?
Well, I said yes because you said that they have to be they have to be exactly 2 vertices that are odd degree.
Yes. So now I have this vertex has an odd degree, and this vertex has an odd degree, and every other vertex has an even degree. So now I must have, according to the theorem that I just claimed without proof, it must be the case that I can start at one of these vertices, end at the other, and traverse every edge exactly once. Is that possible? So let's see. Well, you can try it and you will find it after you try it a couple of times. So let me tell you where it is. So this is the traversal here. You start here, B, so here's the final result. So you do indeed have a way of traversing this graph in such a way that you start at this vertex, end at this vertex, and you've covered every edge.
Professor.
Yes.
Does it matter that we started from the vertex that's odd degree and we ended to the one that's odd degree?
Yes, that matters. It may not matter which one. You may find a different path, but it does matter, yes. So every vertex of an even degree must be internal. You cannot have a vertex of an odd degree inside the path. So you must start at an odd vertex and end at an odd degree vertex. Yeah, that is true. But here you can find a different path. So you didn't have to start. You can start at D and find a path. So it's just one path. So the rest, okay, so the rest you can skip. Actually, you don't really need these slides. There are other examples where using graphs it's easy to solve some sort of puzzles. So there's an example of a puzzle there where it's kind of difficult to see the solution, but the moment you model it using a graph, the solution just jumps at you. So it's just, this was meant as an introduction to graphs, these slides, and seeing how useful a tool graph is, a modeling tool is to solve problems. Okay, now we're not done at all. There's more that I wanted to say. So we're not done with chapter 10.5. We want to talk about Hamiltonian traversals. This is different from Eulerian traversals, but I'll let you get started reading that chapter first, and then we'll talk about Hamilton next time, and I'll postpone the due date of the homework assignment.
Just a quick question. So we're calling the Eulerian path, but it's a trail. Is that
yes. A path. The reason I'm now saying path, and you're absolutely correct. I should if I were to stick with that terminology that I gave in the beginning, I would be using the term trail. Yes, but the text now. But I also want to be consistent with the textbook, and the textbook uses slightly different terminology. It calls that a path. Right? It calls it a Eulerian path.
Yeah. Okay. So I just wanted to make sure.
Yes. But but you're absolutely correct. But from the context, it will normally be clear. So that's why we kind of have to talk a little bit more than necessary when we don't have established terminology. So every time I talk about the traversal, then I say that every edge must be covered exactly once. So I insert that phrase in the explanation. So which is kind of a mouthful to say, but just for the sake of clarity, it makes sense to spend an extra second or two in uttering that phrase. All right, so but makes sense, right? All this. Okay, so now let's go back to, here's what I want to do. Now I want to find the textbook here somewhere, and I want to return to the graphs. So we'll talk about Hamilton next time. So we'll take a break from these traversals, and I want to talk about here. Let me find a textbook example. There's a textbook here. Now, chapter 10.4 that deals with connectivity. We're not covering everything there. But we're covering everything in chapter 10.5. So but please, when you read chapter 10.4, please do not skip the example I'm about to do. I want to do an example from the book now. And that example is example 15 from the book. And I want to explain it very clearly, what's happening there. This example has to do with finding the number of paths of a given length in a graph, okay, using the adjacency matrix representation of a graph. So let me draw this graph that you see there in the book. You have or should I use a book example or something more interesting? Let's start with a book example. D, C. And you have this. Okay, so let me ask you first, how many paths of length 2 are there from A to D? So here's A, here's D, Well, what I mean by a length of a path, first of all, if that's not clear, you should be stopping me now and asking me, what's the length of the path?
The number of edges.
The number of edges on the path. So I start at A, and I end at D. First of all, there's no path of length 1. There's no direct. The path of length 1 is always just one edge. So there is no path of length 1. Okay, so if I write down the adjacency matrix, which we will in a second of this graph, we'll see that the entry that corresponds to the row headed by A and column headed by D, for example, is going to be a 0. There's no path between them. There are no paths of length 1. But how many paths of length 2 are there?
2.
Well, there's this one, and there's this one, right? Okay, so I have 2 paths of length 2. How about how many paths of length 3 are there from A to B? Well, first of all, are there any paths of length 3 from A to D?
No.
Okay, how about from A to B?
1.
Oh, well,
there's 1, right?
2,
well, okay, so
3.
yes. So here's 1, right? But this also counts as a path. This 2, 3, and then I'm sorry, 1, 2, 3. That also counts as a path, right? So what else?
A.
1, 2, 3 also counts as a path.
Yeah.
So we've just counted 4. So let's see what happens. So now here's the claim that I want everybody to see in the next like 10, 15 minutes. That the adjacency matrix of this graph gives me enough information to determine the number of paths of any length in this graph. And we'll be making a connection now with the way of multiplying matrices, the definition that we have. Everybody remembers how to multiply matrices. And we have these row by column, the scalar product that we had of a row by a column. We multiplied those terms, added them up. That's called the scalar product, but whatever. We have a way of finding each entry in the product of 2 matrices. Now, this way of finding those entries of a product of 2 matrices will correspond now with the number of paths of a given length. And this is, admittedly, the last 2 sentences I've said are vague. And my goal is now to clarify this so that everyone's on the same page with counting the paths of a given length in a graph. So let's get started. First thing I want to do is I want to write down the adjacency matrix of this graph. And the adjacency matrix of this graph, first of all, I have 24 adjacency. Why did I say 24 adjacency matrices for this graph? I could write down. Why did I say that?
It depends on what.
Yeah, it depends on
A, B, C, D, B, C, D, A, whatever. Yeah.
Yes. So if let's use this A, B, C, D ordering. Okay. And let's write down the adjacency matrix. Well, that's pretty. So there's a path from B. There's a path to C. Then that's 0. So I have this. Then I have from B, I have to D. So I have this. And finally, from D, I have this and that. So that's the adjacency matrix, right, of this graph. Nothing new there. Okay. And again, notice that there's no path from A to D, let's say. A to D, there's a 0 here. There's no path of length 1. There's no edge from B to C. Nothing here. So this entry is 0 and so on. So that's old story. Now let's see what's A squared. This should take us a second to compute A squared. Okay, so A squared is going to be that times that. And what's the result? So help me out. This should take 2 seconds to compute, please. Okay. Okay, so what's the result? It takes 2 seconds to compute because you have a bunch of rows and a bunch of columns. What's this entry here? One entry. Take this row. Yes. What is this?
2.
2, right? What's this entry here?
2.
2? No. Okay, so the first row by the second column.
0.
Yeah, 0
Oh,
times
yeah,
1
yeah.
plus. So every time, every one hits a 0. So it's going to be a 0.
And then another 0.
0. And then this one is 2 again, because, this guy by that guy, again, you hit 1 and 1 hits, those hit these ones, and then zeros are outside. So you get a 2. Anyway, let's do, we don't really need all entries here for the point that I'm trying to make, but since we're at it, let's compute the whole matrix. What is the entry in the second row? The entries in the second row. This one is 0, 2, 2, 0. Am I correct?
Yeah.
And from symmetry considerations, if you fill out the rest, you can either compute or just argue by symmetry, whatever you prefer to do. You'll get this matrix. This is A squared. Okay, this is A squared, this matrix here. Now, let's look how many paths of length 2 are there from A to A.
2.
2.
Yeah.
Okay, so
for length 3, do we have to multiply it one more time?
yes, but I want to ask the question: why does it work? We want to get insight. I mean, I don't want to tell you, okay, so compute the power of the adjacency matrix, and then you'll get the path of that's not a math class. We want to see why this works. Okay, so since you've asked about A cubed, let's just write that down. So A cubed is going to be this guy multiplied by this guy, which is A squared from either side. Okay, so this is what we have. So let's multiply those, by the way, since we're at it. Let's make that guy purple. What's the result?
0. The first row, row is all zeros.
Mm-hmm. Oh, all zero?
No, the first element is 0.
Okay. All right.
The second is 4.
The second is 4. The second is indeed 4.
The third is 4. And then 0.
Okay, and then here. Oh, hold on. Yeah. You might detect the pattern now, but so we're not that concerned about this pattern. So there's something else we want to see. But yeah, you see it's a nice pattern emerging, but that has to do with the structure of the graph. Admittedly, it's nice. But let's, while we're at it, let me also compute A to the 4th. How much time do we have? Yeah, we have time. A to the 4th is going to be, so far we're just, so I want to take this matrix and square it. That's going to give me A 4th. Ooh. Okay, so that's that. Times that is going to give me A to the 4th. And what's that going to be? 2 to the, so 8, 0, 8. Let me write it down so we don't have time. So you'll compute it. Everybody knows how to compute these things. You'll get this. So you'll compute this. Okay, you can either compute it if you like it that way, or you can argue from symmetry considerations. Once you have a couple of entries, you should be able to figure out the rest, whatever works for you. But these are the powers of those matrices. Right? Now, let's start here. A squared here. How many paths of length 2 are there from A to D? Let's take this one, or A to A, doesn't matter. A to D. 1 guy, 2 guy. This 2 tells me that there are 2 paths. How many paths from A to A? Here's 1. Here's another one. There's no other paths. This 2 tells me that's the case. Same thing is happening from B to C. How many paths are there from B to C? Well, here's 1 path from B to C. Here's another path from B to C. So of length 2, where is the 2? Here's the 2. When I computed a squared, I'm talking about the paths of length 2. When I'm computing a cubed, this cubed, then I'm talking about paths of length 3. So apparently between A and C, let's say, there are 4 paths of length 3. A to C, well, here's 1, the Zorro path. Here's 1 more, that's the second path. Okay, here's 1 more, that's the third path. You get the idea. So I have 4 paths there. Finally, let's look, well, that's too much to count. A4, if I wanted to count the number of paths of length 4, then I would look at the 4th power of this matrix, and an entry of 8 here will tell me that there are really 4 paths of length 4 from A to itself, to A. Here's 1. 1, 2, 3, 4. I started at A, ended at A. Here's another one. 1, 2, 3, 4. Started at A, ended at A. And so on. So you get this path also. Started A, ended. So you have 8 such paths from A to A. Okay, so now everybody's getting a sense that this is kind of working. But now I want to justify why that's the case. Why should we know how to multiply matrices? So you take a row, you take a column, and you multiply them like that, and then add them up. So what does this multiplying and adding those things up, how does that sequence of operations give me at the end of the day the number of paths of length 2? Let's stick with the squared, and then the rest of the examples will be clear from this. Let's just go with the squared. So what am I doing when I'm computing? Let's stick with, let's go red, and let's talk from B to C just for concreteness. So here's B, and here's C, and I know that I have 2 paths. This guy, and this guy. Okay, so this one path, the second path. Okay, so I have 2 paths, and the way I computed this 2 was to take this row and multiply it by this column, and multiply it by this column. How did I multiply it? What was I doing when I multiplied this one by this one? Then
we're adding the neighbors, kind of, not name. We're trying to find the neighbors, like what is the common neighbor that they have?
Okay, yes. Okay, so I want everybody to be clear with this. So from where am I? From B to C, B to C, from B to C. In A squared, we're talking about paths of length 2. So here's a path, B. When I multiplied this 1 by this 1, so I have 1 times 1 plus 0 times 0 plus 0 times 0 plus 1 times 1. This 1 times 1 here corresponds, my claim is, to a path from B to A, this term, and then this term corresponds to, hold on a second. Yeah, B to A, and this term corresponds from A to C. A to C. So my claim is that this term here, this piece of the entire sum, corresponds to one of the paths from B to C. Did this make sense right now, what I just said? And there are multiple paths like that. So to get from B to A to C, that was that path. Now, this 0 times 0, like this 0 times that 0, what does that correspond to?
Corresponds to get from B to B, and then from B to C.
Yes, exactly. So let me count. So B, here I have A, B, C, D, and here this column corresponds to C. So this term here, this term, this 0 times 0 corresponds to getting from B to B, and I'm sorry. So B to B, and then yes, and then from B to C, right? From B to B, there is no path. There are no loop. There is no loop, self-loop. And from B to C, hold on a second. Yeah. And from B to C, there is no edge. So that's why I have a 0 here, for there being no edge from B to C. And why I have a 0 here? There's no way of getting from B to B. Now, what's happening here? So help me out, somebody who is trying to grok this. This term, what is that? Which path does this term correspond to? So I'm multiplying this entry, which is a 0, by this entry. What is this entry all about? It's about a hop edge, a hop from B to C. This is about a hop from where to where?
B to C, or B to...
You're correct in to C, but from where? From C to C, this entry.
Yeah.
From C to C. So this 0 corresponds to C to C. There are no paths from C to C. There's no loop. This 0 here, this 0 corresponds to B to C. There's no path from B to C. That's final term. This will make it completely sentient if you're still missing it. So the last term here is 1 times 1. So 1 times 1. So my claim is that this, let's go here, corresponds to B to somewhere, and I should end up in C. What's in between here? This term. What is it? D, right? Is that what you said? Yeah, it's D, right? So B to D, and then D to C. This is D to C. Make sense? This term. So this is D. Is there a path from B to D? Oh, yes, there is a path from B to D. There's that edge. Is there a path from D to C? Yes, there is a path from D to C. There's that edge. So that's why I have it 1 times 1. And because both of these edges are present, and that's what the adjacency matrix told me, those edges form a path. Both of them are present. So I have a path from B to C that goes through D. And that's the term that tells me, the presence of that term tells me about that particular path. So the point I'm trying to make here is that each term in that product, in that scalar product of row times column, notice that in linear algebra will imbue this with a completely different sense. But here it's just multiplying these terms and adding them up. And each term corresponds to a particular path from B to C. Term is a particular path. And when I sum up the terms, I get the sum of all paths possible. Make sense to people? So please think through this. It will make complete sense once you think through it. Here's one way why, this is probably a first way, why matrix multiplication this way kind of makes sense. So in this context, this rule of multiplying matrices counts for the number of paths of a given length. I take the adjacency matrix to the 15th power. I find paths of length 15 in the graph everywhere, from any vertex to any vertex. So I have like 4 by 4 matrix. So a to the 15th is some 4 by 4 matrix. By the way, it's a good idea to predict what's happening to this matrix as you continue squaring it. There's a nice pattern that emerges, and that has to do with the structure of the graph. That's a separate issue. But if you take this matrix to the 15th power, you'll get all possible numbers of paths of length 15 from any vertex to any vertex. For example, at this position, you'll have all the paths from C to D right here. Whatever the entry there will be in A to the 15th, that's the number of paths from C to D of that length. Okay, let's wrap up here. Please read sections 10.5 and 10.4